The singular value decomposition is being widely used for various engineering problems. In this section, we'll apply it for least squares problems. Let's begin with a recall. That is a definition for the least squares problem. A is an m by n metric. M is larger than or equal to n. B is a vector in Rm. Then the least squares problem is to find x hat in Rn, which minimizes the L2 norm of the difference. So x hat is the minimizer of the norm. We can equivalently write it in this form. We have here power 2. Once one is minimized, then the other one must be also minimized. So these two problems must be equivalent. X hat is called a least squares solution of the system Ax equals B. When A transpose A is invertible, then the equation linear system has a unique least squares solution for every choice of B in Rm. It can be solved by the method of normal equations. The unique least squares solution x hat is given by this equation. X hat is A transpose A inverse A transpose B. This metric plays the role of the inverse of A. For example, assume A is a square metric invertible. Then the solution can be gotten in this way. X is now A inverse of B. The form is the same. X is the metric times B. So this metric is playing the role of the inverse of A, but it's not really inverse. A doesn't have inverse if m is larger than n, but it plays the role of inverse. So we try to give the name pseudo inverse. This metric is called the pseudo inverse of A. And if A has the singular value decomposition U sigma V transpose, then this metric, after simplification, you can reach at this product V sigma inverse and U transpose. For this metric, we try to use the notation A plus, which is the pseudo inverse of A. Let's see the example. Find the pseudo inverse of A for the given 30 by 2 metric. Earlier in example 9.7, we got already singular value decomposition U sigma V transpose. And the pseudo inverse of A must be V sigma inverse U transpose. So from here, there is a V transpose. Now V is transposed, and sigma inverse is just along the diagonal. We take reciprocal, and U transpose. The transpose of U is here. Once we multiply, then we can reach out this metric. So for when we try to solve a least square problem, then now the solution is just simply metric transformation from the given source vector. Now here we summarize solving the least square problem by using singular value decomposition. Okay. Now A is an m by m metric. M is larger than or equal to n. Now with rank of A is k, k may be smaller than n. It can be the same or smaller than n. Once smaller than n, then A transpose A is not invertible. But anyway, in any case, by using the singular value decomposition technique, we can solve the least squares problem. We start with the singular value decomposition of the given metric, and A is U sigma V transpose. U has property. U transpose U is identity. This property implies that the metric is L2 norm preserving. That means for U x for the vector, norm is same as now x norm. The transformation through U does change norm. In fact, angle preserving and dot product preserving, those properties are granted for such metric. Ax minus b, A is the same as U sigma V transpose. So we put here, and we multiply U transpose, of course, and now U or U transpose, it doesn't matter, just norm preserving. So we multiply U transpose, and then it will disappear, and we have U transpose. We recheck this term. To deal with this term more conveniently, we introduce new variables. Z is this one, V transpose X, a vector, and C is U transpose B, that is C. So that we say this C and this is C. Then Ax minus B, 2 norm, can be written in this way. Now, this sigma has sigma 1 and then sigma k. The rank of A is k, and then later terms must be 0, like that. And then here now we have z1 and z, that is now n, equals. We use C notation, so the C1, there's a negative, C1 to Cn. Then if we multiply in this metric and vector, then it's sigma 1, Z1 minus Z1, and sigma 2, Z2 minus Z2, up to K, that is a sigma K, Zk, minus Zk, that is exactly this one, in measuring 2 norm, square sum, and half power. But from K plus 1, now this is 0, so that multiplication will be 0. Only the term we can consider as a C values. So that from K plus 1 to n, we have Ci squared. So this whole thing is exactly this norm. Now we have to minimize the norm. The only way is to make this term 0. Square is always non-negative. We try to make it 0. So from 1 to k, we can decide Zi is Ci over sigma I. Now for remainder part, from zk plus 1 to zn, we can decide arbitrarily. No matter how we decide, it doesn't matter, always the same. Once it is 0, then it's minimum. And for the later zi's, and arbitrarily we can choose. Okay, let's put arbitrarily, but later we'll decide this one more smartly. But anyway, we decide the z, and first k component from here, and later n minus k components, they are arbitrary. Let's assume we determined. Then, now once the vector z is determined, then from the definition, z is v transpose x. So we multiply v, then vz equals x. X hat can be found through this equation. Now the least squares error in this case is exactly the same as that one. This will be 0, and this is remaining part, which is the error. So we have this error. Okay, here, particularly for the arbitrary part, we need a little bit of a strategy so that we can deal with the problem more effectively. When z is obtained, as in earlier, it is better to choose 0 for the arbitrary part, so that z will become, for the first k components through that one, we can find first k components, and then for remainder part, we just put 0. In this case, z can be written as this one. Now, that is sigma k plus, the k means that only k component, and of course that is pseudo inverse, so that we consider only k component and its reciprocal to make the pseudo inverse. Sigma k plus c, okay, this one, and times c will make that one. And what is c now? C is U transpose B. Okay, so that we reach at this term. Now, in summary, we can write in this way. X hat, the least square solution, is a VZ, and now Z is the same as this term, so we reach at that. So after getting the least squares, after getting the singular value decomposition, the least square solution can be found through U transpose multiplication, and along with a choice k, we try to make pseudo inverse of sigma k and multiply, and then v is multiplied. Then we can get the solution. The x hat involves no component of the null space. This portion is null space. You can choose arbitrarily, but we choose 0, which means that we exclude the null space components of A. So there's no null space component is involved in this solution. In this case, the solution is better in most cases, rather than arbitrary choice, which means that arbitrarily you are trying to involve null space component. So it is now not really a smart choice. really smart choice is this arbitrary part must be 0. Okay. Okay. Now, once we exclude the null space, then now we can say that such least square solution is unique under the condition that null space is excluded. We have a remark. When rank of K, rank of A is K, K is the same as N, which means that it is a full rank, then the matrix K is N and pseudo inverse is really inverse, so that we reach at the pseudo inverse of A. Okay. Now, once K is smaller than N, then A transpose A is not invertible. The rank of A means K means that there are only K independent columns in A, but there are N columns, but only K columns are independent. So the A transpose A is not invertible. However, this AK plus, if we define it this way, then that places the root of the pseudo inverse of A. So it is often called the kth pseudo inverse of A. It is taking only K component, and so that we say that is the kth pseudo inverse of A. For some least squares applications, although A has full rank, the kth pseudo inverse may give more reliable solutions. For some K less than N, sometimes way smaller than N, but you can get more reliable solutions, more accurate solutions. Finding such a K is one of interesting research topics in data analysis. Okay, that's the end of the section. Thank you.